Hey everyone, this is our first set of notes for Unit 5. This unit will go into some of the stuff y'all learned last year and hopefully dive a little deeper into a lot of it. So today we're talking about atomic structure and a little bit of history of the atom. So this is stuff that I actually really enjoy and really love. So there's no math involved today. We'll get into that next class. So for today, it's just kind of listen and learn, and hopefully you will remember some of this stuff from last year. So we're going to be talking about a lot of scientists that contributed to what we know today about chemistry. So our first one is Democritus. He was the first to theorize that all matter was composed of atoms. He didn't say atoms necessarily. It was a Greek word called atomos, which means dividable or not dividable or divisible. Democritus' ideas were crushed by another Greek philosopher named Aristotle. So Aristotle asked Democritus these questions. If we're made of atoms, what holds us together? Why can't we see these atoms? And why don't we fall down or fall apart like a bag of marbles? So all really good questions if you think back to that Greek time period. Democritus was unable to answer these questions, so people continue to think that matter was continuous. Your body, the world around us, was all one continuous piece. That was kind of continued for many centuries until some more people came along and questioned that. During the Middle Ages, science was kind of lost to the world. If you think back to history classes, there was a whole lot going on during the Middle Ages all over the world. So science wasn't really at the front of people's minds. The only science that was done was performed by the Arabs or the Moors out of Africa that eventually conquered Spain. They traveled from the Middle East to Western Europe, carrying the great library of Alexandria with them. While the plague and the Dark Ages were killing millions, these people had everything. The Moors had running water. They had the beginnings of dentistry. They were able to read and write and practice geometry and calculus. They had breweries. There were complex gardens, complex agriculture going on. So they were really kind of doing super well compared to the rest of the world. Science didn't really become popular again until people started challenging the church. During the 17 and 1800s, scientists were discovering concepts and relationships. So scientists were doing large, observable, basic experiments where we could see things happening in real life. They weren't doing tests with microscopes or computers. They were doing experiments with what they had. So stoves, pots, ovens, any basic glassware they could find. Anything that they can observe and then explain in real life. So then we have Joseph Priestley. He prepared pure oxygen. He decomposed mercuric oxide into mercury and oxygen. He basically invented soda. He discovered carbon dioxide and nitrous oxide, which is just laughing gas. Joseph Priestley noticed that gas produced by heating mercuric oxide burned a candle very brightly. He called the air perfect air. People thought that, I'm going to butcher this word, phlogiston, not going to say it, was a substance that was in materials. When substances burned, they released this gas, which caused the flames to go out. So he was trying to figure out what was in this air that was causing the flames to go out. He basically discovered oxygen, but he didn't know it at the time. It wasn't called oxygen. It was just called this perfect air, as he theorized. Then we have Antoine Lavoisier. You should have learned about this guy last year. He lived during the French Revolution. He was a very, very smart scientist, but he was actually a tax collector. He eventually had his head chopped off during the revolution because of royalty. He proved the substances did not get off this unknown chemical, but it was oxygen. They were using oxygen to burn. He burned metals in the air and he weighed them before and after to see what was happening. So the substance that weighed more after, it was because they were combining with this oxygen and gaining mass. By weighing before and after, Lavoisier came up with the law of conservation of mass, which everyone should know by now. It states that matter cannot be created or destroyed in a chemical reaction, but it can be converted from one form to another. The extra mass came from the oxygen in the air, which he later measured by reheating the compounds that was formed. Next, we have Joseph Proust. He examined copper carbonate. No matter the amount, whenever decomposed, it always yielded 5.3 parts copper, 4 parts oxygen, and 1 part carbon. He came up with the law of definite composition. It said all substances are composed of definite amounts of each element, no matter how much or how little of the matter there is. So this specific compound, copper carbonate, always has 5.3 parts copper, 4 parts oxygen, and 1 part carbon. Kind of like H2O always has 2 hydrogen and 1 oxygen. Next, we have John Dalton. So he was actually a school teacher. You should have learned about this guy last year as well. He devised the law of multiple proportions. It stated that when 2 elements form more than one compound, they come together in whole number ratios. So think of when we balance equations, those are always whole number ratios. Carbon and oxygen are the main things that he talked about, and they form 2 specific compounds. You could have carbon dioxide, so CO2, or you could have carbon monoxide, which is just CO. In carbon dioxide, the carbon and the oxygen combine in a 3-part to 8-part mass ratio. In carbon monoxide, CO, they do so in a 3 to 4-part mass ratio. So that's just saying the mass, if you were looking at the mass ratio of each one, that's how it would look. It seems obvious, I guess, to people nowadays. Back then, it was not so obvious. They didn't know what was making things come together to form these reactions. They didn't even know what an atom was or if it existed at all. If compounds come together in ratios, they must be made of smaller pieces. Dalton theorized that these substances were made of atoms. This led to the atomic theory of atoms. So this is super, super important in the history of atoms. You can also kind of go back and remember Dalton's postulates. This is where that came from. So I have the atomic theory. It says that all elements are made of tiny, solid, indestructible particles known as atoms. All atoms of a given element are the same. Atoms of different elements are obviously different. So a carbon is different from oxygen. Atoms of different elements form compounds in whole number ratios. So you could have 1 atom, 1 to 2 atoms, or whatever. A chemical reaction does not change the atoms themselves, only how they're combined to form compounds. It took almost 2,000 years before the idea of the atom came back. So all the way from Democritus to Dalton was about 2,000 years. Dalton was slightly wrong. Atoms are not solid or indestructible like marbles. They contain different parts, which we know nowadays. Scientists didn't know this until the parts of the atom were discovered. What part of the atom do you think was discovered first? It was the electron. So think to yourself, why do you think it was the first part of the atom to be discovered? Even just looking at this picture can kind of give you a hint. The electron is on the outside of the atom. The electron is the only part of the atom that can be added or removed. So, of course, this is going to be the easiest one to discover if it's being added and removed constantly from different compounds or different atoms. The electron's tiny and it's very light or lightweight. That's why it can be so easily added or removed. This also is going to help their knowledge of electricity, so moving electrons. technology wasn't that great hundreds of years ago, so it took a while to discover the electron. In the early 1800s, there was lots of basic work with electricity. This is kind of when it all began. They realized that matter has a charge. There's two types of charges in the world, which we all know. We have positively charged objects and we have negatively charged objects. In the early 1800s, Ben Franklin is the first to come up with the names positive and negative and to discover that matter had a charge. He didn't know these charges were part of an atom. He didn't even know yet that atoms had existed. So here's a few of the experiments that helped discover electrons. We have the cathode ray. This should sound familiar. It's just an evacuated tube containing two metal electrodes connected to a battery. So if you look at this picture, I have the battery at the top, and then I have an electrode at each end. One will be a positive, one will be a negative. William Crookes designed this in 1879, so it could also be called a Crookes ray. The cathode ray on the inside will glow bright green. He was convinced that this beam consisted of charged particles. J.J. Thomson, another familiar name, in 1897 used a cathode ray and two charged plates above and below the beam. The beam was attracted to the positive plate, but it was deflected from the negative plate. So he said that the beam was made of negatively charged particles called electrons. That's where the name electrons coming from. He was looking at electrons, which are part of the atom. These electrons can easily be taken off the atom and used as electricity. So here's what happened. He used this cathode ray to shoot beams. The beam went towards the positive plate because the beam was made of negatively charged particles called electrons. He also saw that a magnet caused the beam to move as well, concluding that magnetism and electricity were going to be related. This allowed him to calculate ratio of electron mass to charge. So he won the Nobel Prize in 1906. Okay. The cathode ray was a precursor to the modern day television. So here's some little diagrams that you're more than welcome to pause and look over if you would like. Okay. Oh, let me go back. No. Okay, so there will be a video on your class website eventually. So just keep a lookout for that of how this cathode ray works. All right, next we have the Millikan oil drop experiment. Robert Millikan in 1909 discovered the charge and mass of an electron. He placed an electrically charged oil drops in an electric field. The oil drops were then sprayed into the upper chamber. Some drops gain negative charge. So this was static electricity. So here's kind of what that looks like. We have a little place to observe what's happening over there on the left. There's x-rays being shot into it. There's a negatively charged plate at the bottom. There's a positively charged plate at the top. And then we have these oil droplets being kind of shot in. Okay. He adjusted the voltage on the plates in the bottom chamber. The negatively charged particles attracted to the upper plate. So remember that upper plate was positive. And it kind of suspended the drops in space. From this, he calculated the charge of an electron, knowing the charge that he had on the specific plates. The smallest change between the two drops was taken to be the charge of an electron. Using J.J. Thomson's mass to charge ratio, Millikan could calculate the mass of an electron too. So the mass of an electron was calculated to be 9.1 times 10 to the negative 28 grams, which is super, super, super tiny and really hard to think about how small that is. The charge of an electron was calculated to be negative 1.60 times 10 to the negative 19. So we just call that negative 1. Okay, so next we have a few experiments that helped us discover protons. Again, we have our cathode ray. So we have Eugen Goldstein in 1886 used the Crookes tube or the cathode ray with holes in the cathode, and he discovered positive particles. So he shot a beam of electrons at hydrogen ions, and here's what happened. The electrons from the atoms went with the beam of electrons to the positive plate. He observed positive particles moving backwards towards the positive plate and going through the holes. So different number of positive particles were produced when different gases were used. This is obviously because each atom has a different number of protons. We know that just by looking at the periodic table. Okay, so here's a picture of kind of what that looks like. So on my left side, I have the positive end, the anode. On the right side, I have the cathode end, which is negative. So my positive ions are going to the right, my negative ions are going to the left. This helped kind of discover protons. So now I know all about electrons, I know all about protons, but there still needs to be someone to pull all this information together and really give us a big picture. So I have J.J. Thomson again. He theorized that these negative and positive particles were actually part of matter and part of the atom. We're all made of charge, he said. He develops the first working model of the atom. This is known as the plum pudding model. This should sound familiar, hopefully. This rejected Dalton's idea that atoms were solid, like marbles, and that they weren't made of smaller pieces. So here's a few examples of this plum pudding model. Plum pudding is like an English type dessert. It's basically a pudding with pieces of plum on the top. So he basically said the pudding part itself was this huge positive, and the plum was little negative pieces, kind of like a chocolate chip cookie, I guess. So here's what that looks like. So people didn't believe in atoms, surprise, surprise, and they didn't understand what things like electricity and light were. This was all brand new information to them. Thomson showed that electricity was nothing more than a flow of little particles called electrons. And electrons, along with protons, make up every single atom and every person, plant, building, object in the universe. So imagine trying to get that idea across to people that have literally never seen or experienced electricity. He also said we're made of charged particles, the same particles that we use for electricity. Okay, so then this guy Henry in 1895, he put a chunk of uranium in a desk drawer with some photographic paper. When he came back after the weekend, the paper had a picture of the uranium chunk on it. He knew the uranium atoms must be giving something off for them to be able to go on the paper like that. He called it radioactivity or radiation. The same year, a guy named William had a similar experience. His uranium actually caused photographic paper to develop in a nearby lab, so it went all the way through the wall and developed on a piece of paper in a different room. He called it X-rays. They're immediately used for medical purposes, so it's kind of funny to think about. Something doctors use every single day was discovered on accident. Was this actual radiation, though? How did this relate to what J.J. Thomson had already discovered? So then we had a man named Ernest Rutherford, who you should also know. He was determined to figure out what this radiation was. He was a physicist from New Zealand. He took a chunk of uranium and set out to determine what exactly it was giving off. He placed it in a lead box. He took 2 charged plates and placed them above and below the beam of radiation that the uranium was giving off, and it then split into 3 separate beams. Okay, so here's a picture of kind of what that looks like. So I have my lead block with the radioactive material inside, which in this case was uranium. And then he had that photographic plate, so it's kind of taking a picture. You can think of like an X-ray. And then I have those negative and positive plates on the top and the bottom. The 3 beams are alpha, beta, and gamma radiation. The beam that goes towards a negative plate were positively charged. He called that alpha radiation. It's actually just a helium nuclei. So there's a picture of what that looks like. So 2 protons, 2 neutrons. It has a charge of +2, has a mass of 4. So just like a helium. They move very slow because they're very, very heavy and they don't have that much energy. Beams that go towards a positive plate are going to be negative. He called that beta radiation. They are actually just electrons, so they have a charge of -1 and a mass of 0. These are going to be moving very fast because remember, electrons are so light and they have no energy because there's no mass. Beams that go straight through are not charged at all. This is your gamma radiation, or sometimes it's called C radiation. It's made of pure energy or pure light. There's no mass. It moves very fast at the speed of light, but this can also be deadly depending on what kind of light it is. So here's a little graph of summing that up, what that looks like. Okay, so why do some atoms give off radiation? Rutherford looked back at his model of the atom for answers. All of the protons are jammed in a tiny little nucleus, and they all have a positively charge, which means they're constantly pushing each other and trying to repel each other. So what's keeping protons in the nucleus to begin with? Neutrons. So the neutron was the last particle to be discovered. Why? Because it has no charge. It's hard to discover something that doesn't even have a charge. It was discovered when James Chadwick noticed that beryllium atoms were giving off some unknown particle when hit with alpha radiation. These were neutrons. They have a special force known as the strong nuclear force that holds the protons together because the protons are always pushing each other out. So the neutrons kind of act like glue to hold the protons in the nucleus. Okay, so here's an example of kind of what that looks like. Without the neutrons, protons would be going all over the place. The neutrons are kind of holding those in. Okay, a couple other things. After lead, which is element 82, there's too many protons in the nucleus, so no number of neutrons with a strong nuclear force are going to hold in those protons. The atoms are going to be too big, so they start just ejecting stuff all over the place to kind of release the pressure. That stuff is called radiation or radioactivity. So that's why when we get to big atoms after 82, there's just all kinds of radiation and radioactivity going on. Most atoms normally have more neutrons than protons anyway to keep those protons in place. So any atom after lead is constantly giving off radiation to kind of relieve that pressure, and it's kind of funny to think about. If you've ever gotten an x-ray done, we wear a lead vest to keep that radiation from going in our body. So anything after lead, it's just constantly giving off radiation. So to kind of summarize all of that was a lot. We know the nucleus contains protons and neutrons. Electrons are orbiting around the outside. Atoms have way too many protons in the nucleus, or the ones that do have way too many protons are going to give off radiation, alpha, beta, gamma, to relieve this pressure. Okay, I know that was a lot for today. Lots of history. Hopefully you knew a little bit of that already, and hopefully you learned a few new things as well. So go ahead and work on the guided practice that is attached in your slides and shoot me an email if you have questions. Bye, guys.